in the previous section, we discussed power series, and we were able to see that a power series represents a function and how to determine the domain of such a function. Now, this all is not much use if you cannot express a function that you already know as a power series, right? Because we're not trying to study power series for their own sake. What we're ultimately trying to do is to be able to represent any function or most functions as power series. So this will be the topic of section 11.9. So first of all, let us recall the very first series that we started our discussion with. So we looked at the geometric series, x to the power k, k from 0 to infinity. And we saw that this series here converges if absolute value of x is less than 1, and it converges to the function 1 over 1 minus x. So this here gives us a representation of this function when absolute value of x is less than 1. And this is a rather useful example. In fact, it's the very first example of us being able to represent any function as a power series. And we are going to exploit it. We're going to use this to represent some further functions as power series. So let us look at example number 1 in this section, which asks to express 1 over 1 minus x squared as a power series. Now, in order to do that, let us think about how 1 over 1 minus x squared differs from 1 over 1 minus x. Well, 1 over 1 minus x squared is the function 1 over 1 minus x with x replaced by x squared. That's what it is, right? So it's this same function where instead of x, which we would normally place there, we place x squared. So if we think of this here as a function, right? This gives the value of this function at point x, then this would be f at x squared, right? So since we already know that the power series represents this function for all x's which are less than absolute, which have absolute value less than 1, it will allow us to represent this here as a power series. So what we will do is we will just take this series k from 0 to infinity and replace x with x squared. So now in order of x, we write x squared and then raise it to the kth power. So this gives the sum k from 0 to infinity, and this expression here is simply x to the power 2k. So what we did here was we replaced x with x squared. Now let us think for a second for which values of x will this series converge. So it is clear that it represents the function 1 over 1 minus x squared. Now for which x's is this equality true? For which x's does it actually represent the function? Well, recall that we obtained it from this series, which converges only if absolute value of x is less than 1. Now, the x here is played by the role of x squared over here. So we can conclude that it converges, the second series converges when the argument, right, the x in this case, or the x squared in this case, has absolute value less than 1. Now, this is equivalent to saying that absolute value of x squared is less than 1. And then you can take square roots of both sides to conclude that you must have absolute value x less than 1. So the second series that we just obtained also converges if and only if absolute value x is less than 1. Great. So using some algebraic manipulations, we were able to reduce this new function to the previous function that we already could express as a power series, and that resulted in the representation of this new function as a power series as well. Let us modify the function even further, and now let us try to express as a power series something even more remote from the original 1 over 1 minus x. So in this example, we will express 1 over x plus 2. So this is the function we would like to represent as a power series, and this is the one that we know how to represent as a power series. So the key will be to reduce by algebraic manipulation this new function to the form of the old function. So here's how we are going to do it. We start with 1 over x plus 2, right? So if you compare these two expressions, you see that in the blue one, the constant comes first. So that we can easily arrange for. We can rewrite this as 1 over 2 plus x. Okay, so this now is a little bit closer to the expression that we know how to represent as a power series. Secondly, we have 1 here, whereas it is 2 over here. So in order to have the constant equal to 1, let us factor out 2 in the denominator. Factoring out 2 results in having 1 plus x over 2. Great. So now if we can represent this part as a power series, we'll just multiply it by 1/2, and that will be the representation of the original expression. Now observe that we would like to have the minus sign in front of x, or in front of the variable part here, whereas here we have plus. So to mitigate that, let us rewrite this as 1/2 times, and then here in the denominator we will write 1 minus x over 2. Great. So now we have something that is basically of the form that we know how to represent as a power series. So if we call again this f of x, then the expression over here is f of minus x over 2, right? Because in place of x, here we have minus x over 2. And so this will produce the desired series representation for us. we have 1/2, and then the series for f evaluated at minus x over 2. The series for f is the sum k from 0 to infinity, x to the power k. Now, in place of x to the power k, we write minus x over 2 to the power k. And this is the power series representation of our original function. We can simplify it further, of course. So we can write it like this. So we can simplify this power here by writing it as one half times k from 0 to infinity. And the power is simply, so let's see what it is equal to. We have minus 1 times x over 2 to the power k here, right? So this being a product of two expressions raised to the power k, it is equal to the product of each of them raised to the power k separately, like so. And then doing the same trick on the second factor, we will have minus 1 to the k times x to the k over 2 to the k. So now this becomes minus 1 to the k times x to the k over 2 to the k. And if you wish, you can put in this factor into the sum to have sum k from 0 to infinity minus 1 to the k times x to the k divided by 2 to the k plus 1. So the k plus 1 comes from combining 2 to the k here with 2 in denominator over here. And this is the representation of our function 1 over x plus 2. Let us determine for which x's this series converges. So to that end, observe that we obtain this series by taking the series, the geometric series for 1 over 1 minus x and replacing x with minus x over 2. So this series here converges as a geometric series. It converges when its argument, so let's say geometric series converges when r, which is minus x over 2, has absolute value less than 1. Let us solve this inequality now. Minus x over 2 absolute value is less than 1. First, we can drop the minus sign. It doesn't change the magnitude. We have x over 2 less than 1. Multiply both sides by 2 here to conclude that absolute value of x must be less than 2. And so our series for 1 over x plus 2 is convergent for absolute value x less than 2. When absolute value x is less than 2. Okay, so now on to the next example. When else can we compute power representations of functions This would be example 3, I think. When else can we represent functions as power series? So let's take the following modification of the previous function and obtain its power series representation. X cubed over x plus 2. So now what we know already from the previous example is that 1 over x plus 2 is given by this series. So let us write it down. So what we know is that 1 over x plus 2 is given by this series. K from 0 to infinity. So then the only difference between this new function and the old function is that we have x cubed in place of 1. So we can take this expression, 1 over x plus 2, and multiply it by x cubed to have this desired function. So then the right-hand side will also be multiplied by x cubed. So let us multiply both sides by this expression of this equality by x cubed. The result is x cubed over x plus 2 is equal to the series multiplied by x cubed. This can be simplified further. Since x does not depend on k, x cubed is a constant in terms of this series. So we can multiply through the infinite series by the constant factor, which results in the answer to this question given by the power series minus 1 to the k, x to the power k plus 3 over 2 to the k plus 1. This series converges when the series for 1 over x plus 2 converges. Right? Because the only difference is multiplying our series by this number. So this number is finite for any x, no matter what the finite x you take. X cubed, that x will be finite. So if you multiply a series that converges by a finite number, you again get convergent series, and vice versa. If the series were divergent, multiplying it by x cubed would still make the answer divergent. So now the conclusion is that this new series for x cubed over x plus 2 converges when absolute value x is less than 2, because this was the answer we obtained in the previous example. And this completes this example 3, which shows one more application of algebraic manipulations to computing power series.